In this video, we're going to talk about electrochemistry. We're going to focus on how the voltaic cell works. We're also going to balance equations under acidic basic conditions, identify the oxidizing and the reducing agent. We're also going to talk about how to calculate the cell potential under standard and non-standard conditions, how to calculate delta G, Gibbs free energy from that, and also the equilibrium constant K. We'll also go over some conceptual examples, some electrolysis problems, and also some stoichiometry, how to calculate the current or the mass that's deposited on the cathode, things like that. So we're just going to do a nice overview of electrochemistry. So let's begin. Let's talk about how the cell works. So let's say that we have a zinc electrode on the left and a copper electrode on the right. Now, the standard reduction potentials for zinc and copper are as follows. This is the standard reduction potential for zinc, which has a voltage of negative 0.76. And here we have the standard reduction potential for copper, which has a voltage of positive 0.34. Now, in a voltaic cell or in a galvanic cell, cell energy is produced. The overall reaction is spontaneous, meaning that the cell potential has to be positive. In an electrolytic cell, you can use energy or put in energy to drive the reaction forward, so the cell potential doesn't have to be positive. It can be positive or negative. A good way to illustrate this is think of a battery. When the battery is powering your cell phone, it is using its own energy to do so, and so it's driving a spontaneous reaction. In that case, when a battery is powering your cell phone or laptop, it's acting as a voltaic cell or a galvanic cell. But when you plug in your battery into the outlet to charge it, well, energy flows from the outlet to the battery, and so it's behaving as an electrolytic cell because it's receiving energy from an outside source. So that illustration can help you to distinguish between a voltaic cell, which is a galvanic cell, versus an electrolytic cell. But what you want to take from this is that, remember, voltaic and galvanic cells, the cell potential has to be positive. It's going to be a spontaneous reaction. Now, here we have a voltaic cell because there's no outside energy source that's driving this system. So if the electrochemical cell is generating its own energy, it's a voltaic cell. Now, here we have standard reduction potentials. Anytime the electrons are on the left side, it's reduction. We need to switch one of these half reactions so that the overall cell potential is positive. If we switch the half reaction for copper, if we reverse it, the cell potential is going to change from positive to negative. And if we add the two, we're going to get a negative cell potential, which is what we don't want for a galvanic cell. So instead, we need to reverse the half reaction for zinc. Notice what happens when we do that. So the cell potential is going to change from being negative to positive. So it's positive 0.76 volts. And so at this point, we can add the two half reactions. If we add them, the electrons will cancel. On the left, we have zinc plus copper 2 plus, and on the right, we have zinc 2 plus and copper metal. So this is the net reaction. And the cell potential for this net reaction, all we need to do is add these two numbers. So 0.76 plus 0.34 is about 1.1 volts. So this is the standard cell potential for this particular reaction. Now, under standard conditions, the concentration of the ions, like the copper 2 plus and the zinc 2 plus ions that are in the solution, the concentration has to be 1 molar or 1 mole per liter. If the concentration is different, the cell potential won't be 1.1 volts. It's going to vary. It might be 1.08, it might be 1.15, it's going to change, but whenever you have a standard cell potential, that means that the concentration of the ions are also standard as well. It's 1 mole per liter. But now let's talk about how this reaction works. So looking at the first half reaction, this is an oxidation half reaction. The reason why it's oxidation is because zinc loses 2 electrons. It gives away 2 electrons. And notice that the oxidation state of zinc increases. It increases from 0 to 2 plus. So whenever the oxidation state goes up, or if electrons are lost, it's an oxidation half reaction. And anytime you see the electrons on the right side, it's also oxidation. Whenever the electrons are on the left side, it's reduction. The copper 2 plus ions are gaining 2 electrons, and so it's reduction. And if you look at the oxidation state for copper, it goes down from 2 to 0. So the oxidation number reduces or decreases, so therefore it's reduction. Now, let's understand what's happening in this electrochemical cell. So the zinc atoms in the zinc electrode are losing 2 electrons. So every atom is going to give away 2 electrons. And so the electron is going to flow from the zinc electrode into the copper electrode. So as zinc loses 2 electrons, it's going to enter the solution as zinc 2 plus. And as the electrons flow towards the copper electrode, the copper ions that are in the solution, well, they're attracted to those electrons. Opposites attract. And so those copper 2 plus ions, they're going to be pulled toward those electrons because there's an electrostatic interaction that pulls the electrons and the positively charged copper ions together. So they're going to accelerate towards this electrode. And so as the copper 2 plus ions picks up 2 electrodes, they're going to deposit themselves as copper atoms on this electrode. Now, the zinc electrode is called the anode, and the copper electrode is known as the cathode. Electrons always flow from anode to cathode. Also, oxidation always occurs at the anode. Zinc is being oxidized into zinc plus 2 as it gives away electrons, so oxidation is occurring at the anode. At the cathode, reduction occurs. Reduction always occurs at the cathode. You can see that the copper 2 plus ions are gaining electrons. Now, notice that the zinc electrode is losing mass. The zinc atoms are leaving the electrode and they're entering the solution. Therefore, the anode always it loses mass, so it gets smaller and smaller. Now the cathode, notice that it's gaining mass. The copper ions in the solution, they're depositing themselves towards the cathode, and so the cathode it gains mass. Now, let's talk about the salt bridge. First, let's clear away some space. So, let's say if you have 3 potential compounds to choose from. Let's say zinc sulfate, zinc hydroxide, and zinc carbonate. Which of these 3 compounds will be most suitable for the aqueous solution that contains the zinc electrode? Which one would you choose? The best one to use is the zinc sulfate solution. And the reason why that's the case is because zinc carbonate is insoluble. It's a solid. And the same is true for zinc hydroxide. So zinc sulfate is the best choice because it dissolves in water. It's aqueous. It's soluble. And so you want to use that. So we're going to use zinc sulfate and copper sulfate for both solutions. Now, the purpose of the salt bridge is to maintain charge balance. As the electrons flow from the anode to the cathode, ions are going to travel through the salt bridge. Now, it turns out that the zinc plus 2 cations, or the zinc 2 plus cations, they're going to move towards the cathode. Cations always travel towards the cathode. Cations are positively charged ions. The anions, like the sulfate ions, anions are negatively charged ions. And the anions, they travel towards the anode, so they move to the left. So make sure you remember that for this particular course. Cations travel towards the cathode. Anions, which are negatively charged, they travel towards the anode. So those are the basics behind the electrochemical cell. That's how it works. But now, let's go back to the reaction that we wrote before. The net reaction, which was zinc plus copper 2 plus, which turns into zinc 2 plus and copper metal. Zinc and copper are in a solid phase, and the ions are in the aqueous phase, which means that they're dissolved in water. So now, how can we identify which one is the oxidizing agent and which is the reducing agent? So in order to do that, you need to find a substance that is oxidized and a substance that is reduced first. So notice that zinc, the oxidation number increases from 0 to 2 plus. So therefore, we could say zinc was oxidized. And for the copper 2 plus ion, notice that the oxidation state decreased from 2 to 0. The oxidation state of any pure element in its natural state is 0. So because for copper it went down from 2 to 0, it was reduced. So reduction occurred at the copper 2 plus ion. The substance that is oxidized and reduced, it's always a reactant. It's always on the left side. So you can't pick one of the two products on the right side. It has to be on the left side. Now the substance that is oxidized is also known as the reducing agent. And the substance that is reduced is also known as the oxidizing agent. The reducing agent is the one that causes the other substance to be reduced. So zinc is considered to be the reducing agent because it causes copper 2 plus to be reduced. And the copper 2 plus is the oxidizing agent because it causes the other substance, zinc, to be oxidized. And so that's why you have to reverse them. So just so you know, metals are usually good reducing agents. And metal ions, sometimes they could be decent oxidizing agents. Nonmetals are usually oxidized agents like fluorine, oxygen gas. Those are oxidizing agents, by the way. So just want to make sure that you understand that particular concept. But now let's go back into the cell potential of this reaction. Now we calculated the cell potential to be 1.1 volts. Using this information, how can we calculate the delta G of this reaction, the Gibbs free energy? The equation that we need is delta G is equal to negative NFE. Now, if we use the standard cell potential, we're going to get the standard delta G value. Now, N is the number of electrons in the balanced reaction. Now, keep in mind, in the half reaction, zinc converted into zinc 2 plus by removing or dishing out 2 electrons. And the same is true for copper. The copper 2 plus ions, they picked up 2 electrons to turn into copper metal. And so therefore, this is the N value, the number of electrons it takes to balance the 2 half reactions. So N is 2. F is Faraday's constant, which is basically 96,485 coulombs per mole of electrons. And E, which is the cell potential, it's 1.1 volts. Now volts, the unit volt is basically joules per coulomb. That's what a volt is. 1 volt is 1 joule per 1 coulomb. And so notice that the units coulombs cancel. And so we're going to get joules over moles. So if we multiply those numbers, 2 times 96,485 times 1.1, delta G is going to be equal to negative 212,267 joules per mole. And so this represents the electrical work that this cell can do. So this cell can perform 212 joules of work using 1 mole of electrons. And so basically this is the electrical work that can be performed by the cell, and that's delta G, the Gibbs free energy. And so that's what it's used for in this particular problem, and now you know how to calculate it. But now, how can we find the equilibrium constant K from this information? But before we do that, let's talk about a few things. In this example, we have a positive cell potential. Whenever the cell potential is positive, the reaction is spontaneous. If the cell potential is negative, it would be non-spontaneous. Notice that when the cell potential is positive, delta G is negative, which is also true for a spontaneous reaction, due to the fact that delta G is equal to negative NFE. So when E is positive, and you multiply it by this negative symbol, delta G is going to be negative. Now what about K? When the cell potential is positive, that means that at equilibrium it's going to be product favored, because that means that the reaction wants to go from the left to the right. It wants to produce products. The same is true when delta G is negative. But what about K? Whenever you have a spontaneous reaction, at equilibrium, it means that it's going to be product favored. And therefore, for a reaction to be product favored, it has to be significantly large. So K is going to be significantly greater than 1. It could be like 1 times 10 to the 5, 1 times 10 to the 12, but it's a very large number. And the reverse is true. If the cell potential is negative, that means that delta G is going to be positive. And so this process is going to be non-spontaneous. So this is non-spontaneous in the forward direction, which means that in the reverse direction it's spontaneous. So therefore, if it's not spontaneous in the forward direction, it wants to go to the left, that means it wants to go towards the reactant side. It's spontaneous in the reverse direction. So therefore, this is going to be reactant favored at equilibrium. And what do you know about K if it's reactant favored? If it's reactant favored, K is significantly less than 1. Keep in mind that the equilibrium constant K is the ratio of the products divided by the reactants. So if you have a high concentration of products at equilibrium, that means K is going to be significantly large. As you increase the value of the numerator of a fraction, the entire value of the fraction goes up. And so when you have a lot of products, K is going to be large. Likewise, if you have a lot of reactants, if it's reactant favored, K is going to be very, very small. It could be like 0.001 or like 1 times 10 to negative 8. When you increase the value of the denominator, the value of the entire fraction reduces. And so that's what's happening here. As the reactants go up, K is going to be significantly small. But now let's go ahead and calculate K for this particular example. The equation that we need to calculate K is this equation. Delta G is equal to negative RT ln K. But the only problem is we need to isolate K. So let's divide both sides by negative RT. And that equals the natural log of K. Now the base of the natural log is base E. And so E raised to everything on the left side is equal to K. This is a property of logs. That's how you can convert an equation in logarithmic form into exponential form. So therefore K is equal to E raised to the negative delta G divided by RT. So let's go ahead and calculate the value of K using delta G. So in this equation, because R has units joules, it's 8.3145 joules per mole per Kelvin. Delta G has to be in joules. If it's in kilojoules, you will not get the right answer. So let's plug it in. E raised to the negative, which was delta G for this reaction was it was negative 212,267, and then R is 8.3145. And let's assume the temperature is the standard 25 degrees Celsius, or 298 Kelvin. So now let's calculate K. So if you type it in correctly, you should get a very large number, 1.607 times 10 to the 37. And we expect that K should be large because the cell potential was positive and delta G was negative. We said that it's going to be product favored. And whenever you have a product favored situation, K is going to be very, very large. And so that's why it's a huge number. So now let's go back to the net reaction that we had before, where zinc reacts with copper 2 plus to produce the zinc 2 plus ion and copper metal. Now, using this net reaction, how can we write the cell notation for this reaction? How would you do it? So what we need to do is we need to start with the oxidative part of the reaction. So we know that zinc is being oxidized to zinc 2 plus. So we're going to start with zinc solid. And then we're going to have a line. And this line is going to separate the solid phase from the aqueous phase of zinc. And then we're going to have a double line for the salt bridge. So as you can see, the first half of the cell notation represents the oxidation part of the reaction. The second half is for the reduction. So we're going to start with copper 2 plus, which is also in the aqueous phase. And we're going to separate the aqueous phase with the solid phase. And so the second side, or the second part of the cell notation, represents reduction. So that's one way in which you can write the cell notation for a reaction. So here we have a cell under non-standard conditions. Keep in mind the cell potential, or the standard cell potential, was 1.1 volts for this particular reaction. And this would be the voltage if the concentration of the copper 2 plus ions and the zinc 2 plus ions, if they're 1 mole per liter. But now notice that the concentration is not standard. So using this information, how can we calculate the cell potential for this reaction when we know it's going to be a little bit different than 1.1? So the equation that we need, the cell potential is equal to the standard cell potential minus 0.0591 over n times log of Q. This is the Nernst equation. Now this is another different form of the Nernst equation, but this is one form of the Nernst equation. It's a simplified form. So using this equation, how can we calculate the cell potential? So the first thing we need to find is Q. And Q is equal to the ratio of the products divided by the reactants. The same way K, the equilibrium constant K, is the products over the reactants. The only difference is Q is associated with the initial concentrations, whereas K is associated with the equilibrium concentrations. But the way you calculate it is the same. Now, we can't include any solids or liquids in the expression for K or Q. So in a reaction where zinc reacts with copper 2 plus to produce zinc 2 plus and copper metal, we can't include copper solid or zinc solid in the reaction. We can only include the zinc 2 plus and the copper 2 plus ions because they're dissolved in the aqueous solution. So since Q is the ratio of the products divided by the reactants, it's going to be the concentration of zinc 2 plus divided by the concentration of copper 2 plus, which is, for copper, it's 10 for copper, and for zinc, it's 0.01. So 0.01 divided by 10, that's 0.001. So now let's plug in everything into the equation. So the standard cell potential is 1.1, and N, we know it to be 2, and then times the log of Q, which is 0.001. So log of 0.001 is about -3, and -3 multiplied by -0.0591 divided by 2, that's about positive 0.08865, and then we're going to add 1.1 to that. And so the total cell potential that you should have for this problem is 1.19 volts. So now let's understand what's going on here. So let's begin with the net reaction. So the concentration of the reactant was very high. It was about 10. And the concentration of the product was very low. It was 0.01. So let's go back to chemical equilibrium, Le Chatelier's principle. What happens if you increase the amount of reactants that are present? Whenever you increase the reactants, the system is going to try to undo the change that you impose to it. So as you increase the reactants, it's going to try to bring it back down. And the only way you can do that is by shifting to the right. As the reaction goes to the right, the amount of products go up and the amount of reactants go back down. And so whenever you have a large amount of reactants, it's going to drive the reaction forward. And as it drives the reaction forward, it becomes more spontaneous. And that's why the cell potential, it increased from 1.1 to 1.19, because we have a large amount of reactants. And the same is true for the products. We decrease the concentration of the products. And so the system is going to try to bring it back up. Actually, hold on. Yes, it's going to try to bring it back up. And the only way it can do that is by shifting to the right. As the reaction shifts to the right, the products will go back up and the reactants will decrease. So increasing the reactants causes the cell potential to go up. And decreasing the products also cause the cell potential to go up. So whenever you have a large amount of reactants or a small amount of products, the cell potential will increase. The reaction will become more spontaneous. Delta G will become more negative, and K is going to be the same. Now, the products, as you increase the concentration of the products, it's going to shift to the left, and it's going to be less spontaneous or more non-spontaneous. But if you decrease the products, it's going to shift to the right, causing the reaction to be more spontaneous, therefore increasing the cell potential. So make sure you understand these concepts, because depending on what type of chemistry class you might be taking, you may be tested on this information. So now, let's say if we're given the cell potential. So we know the standard cell potential. It's always going to be 1.1 volts, and that's not going to change. But what if the cell potential of this reaction, the non-standard cell potential, let's say if it's 0.97 volts. With that information, how can you find the ratio of the products to the reactants? Basically, the ratio of the zinc plus 2 cation to the copper plus 2 cation. How can we do that? Basically, this is equal to Q. Q is the ratio of the products divided by the reactants. So we need to find Q. So starting with this equation, E equals E naught minus 0.0591 over N log Q. So we need to isolate Q. So the first thing we should do is we need to subtract the standard cell potential. So E minus E naught. And then what we're going to do next is we're going to multiply both sides by N, and at the same time we're going to divide by negative 0.0591. So on the right side, the 0.0591 will cancel, and n will cancel as well. But we're still going to multiply this by what we have on the left side. So we're going to have n times E minus E naught divided by negative 0.0591, which equals log of Q. And so now log has the base, or is in base 10. So to solve for Q is going to be 10 raised to everything we see on the left equals Q. So Q is equal to 10 raised to the, now what I'm going to do is I'm going to distribute this negative sign into this term. So if I multiply top and bottom by negative 1, I won't have the negative on the bottom. Instead, this E is going to be negative, and this E naught is going to be positive, so I'm going to reverse it. So it's going to be 10 raised to the n times positive E naught minus E divided by positive 0.0591. Okay, so now that we have that, let's calculate Q. So Q is equal to 10 raised to the n, which is 2. The standard cell potential is 1.1 minus the non-standard potential, which was 0.97. And we're going to divide that by 0.0591. So you should get 25,080. So this is the ratio of the products to the reactants. So the ratio between zinc 2 plus and the copper 2 plus ions is 25,080. Now let's say if you want to find the ratio of the reactants to the products as opposed to the products over the reactants. So if you want to find the ratio of copper to zinc, all you need to do is flip this number over 1 or under 1. So it's going to be 1 over 25,080. So that's going to be a very small number. 3.99 times 10 to the minus 5. So looking at this number, the 25,000 means that there's a lot of products relative to reactants. So this is a product favored system. So now let's go back to our net reaction. And let's see what is going on here. So if Q is very large, that means we have a lot of products and a very small amount of reactants. So if we increase the products, will the reaction shift to the right or to the left? If you increase the concentration of the products, it's going to shift to the left. And as it shifts to the left, it becomes less spontaneous. And that's why the cell potential, it decreased from 1.1 volts to 0.97, because we have a product favored system. We have a high ratio of products to reactants. So whenever you have a large amount of products and a small amount of reactants, the cell potential will decrease. And the reverse is true. If you have a large amount of reactants and a small amount of products, the cell potential will increase. So that's all I want to say about that. One thing I do want to mention is that notice that the cell potential, the non-standard cell potential, is dependent on the concentration of the reactants and the products. So if you change the concentration of the reactants or the products, the non-standard cell potential will change, not the standard cell potential. This is going to be relatively constant. Now the same is true for delta G. The non-standard delta G value will change whenever you change the concentration of the products or the reactants. However, the standard delta G value will be constant. Now K, the equilibrium constant K, only changes if the temperature change. If you change the concentrations of the products, the equilibrium constant K does not change. It remains constant. So you've seen this equation, delta G equals negative RT ln K. But notice that this is the standard delta G value, not the non-standard delta G value. So K is going to remain constant if the temperature is constant. K is only dependent on temperature. So if you do not change the temperature, K is going to be the same, regardless if you change the concentration of the products or the reactants. And if you do change the concentration of the products or the reactants, the standard cell potential will be the same, and the standard Gibbs free energy will be the same. So if this is the same, K is going to be the same. However, the non-standard cell potential and the non-standard delta G value can change if the concentration of the reactants or the products changes. So now let's work on some stoichiometry problems as it relates to electrochemistry. So here's a typical problem that you might see. A current of 1.25 amps passes through a solution of copper sulfate for 39 minutes. Calculate the mass of copper that was deposited on the cathode. So let's go over a few things. Q is equal to IT. Q represents the charge, and the charge is measured in coulombs. I represents the current, which is measured in amps, and T is the time in seconds. So what you need to know is that 1 coulomb is equal to 1 amp times 1 second. And the second thing you need to know is Faraday's constant. Faraday's constant is 96,485 coulombs per 1 mole of electron. Now, in the conversion, I'm not going to write coulombs. Instead, I'm going to use amps times seconds in place of coulombs. So let's go ahead and begin. So the first thing we need to do, we need to convert minutes into seconds. So there's 39 minutes. And in each minute, there are 60 seconds. So the units minutes cancel. And then we're going to multiply this by the number of amps. So we have 1.25 amps. So now that we have amps and seconds, we can convert that into moles of electrons. So there's 96,485 coulombs, or amps times seconds, per 1 mole of electrons. Now we need to convert moles of electrons into copper, and we need to understand the half reaction for copper 2+. So in copper sulfate, we have the copper 2+ ions, and it's going to pick up 2 electrons in order to become copper metal. And when that happens, it can deposit itself on the cathode. Keep in mind, the mass of the cathode increases, the mass of the anode decreases. So notice the ratio between copper and electrons. It's a 1:2 ratio. So for every 2 moles of electrons that passes through the solution, we can say that 1 mole of copper will be deposited or plated onto the cathode. So now the last thing we need to do is convert moles into grams. So we need to reference the periodic table. And the atomic mass of copper is 63.55. So which means that there are 63.55 grams of copper per 1 mole of copper atoms. So let's focus on the units now. We see that the units seconds cancel, and the units amps cancel as well. And moles of electrons cancel, and moles of copper cancel. So we're left with grams of copper. So now all we need to do is the math. So 39 times 60 times 1.25 divided by 96,485 times 63.55 divided by 2 is about 0.963. So that's how many grams of copper were deposited onto the cathode. So the mass of the cathode increased by 0.963 grams. Number 2. The mass of the zinc anode decreased by 1.43 grams in 56 minutes. Calculate the average current that passed through the solution during this time period. Now, in the last example, we had the time in minutes and the amps, the current in amps, and we were able to calculate the mass in grams. Now we have the mass in grams and the time. We need to find the current. So let's start with 1.43 grams of the zinc anode. And let's convert it into moles. The molar mass of zinc, let me consult the periodic table, is about 65.39. So there are 65.39 grams of zinc per 1 mole of electrons. Actually, per 1 mole of zinc atoms. That's what I meant to write. Now we need to convert moles of zinc into moles of electrons. And for the zinc half reaction, because we're dealing with the anode, we know oxidation occurs at the anode. So it's going to be written this way. But the important thing is the molar ratio. And we can see that the molar ratio is 1 to 2. So that means that for every 1 mole of zinc that is displaced into the solution, 2 moles of electrons passes through the wire or through the solution. Well, technically, the electrons don't really pass through the solution. They travel through the wire. So I guess I should have rephrased this problem in a better way. It's the ions that actually passes through the solution, but the electrons, they travel from the anode through the wire to the cathode. So now let's use Faraday's constant to convert from moles of electrons into amps times second. So 1 mole of electrons is equal to 96,485 coulombs, but instead of writing coulombs, I'm going to write amps times seconds. Now this is the part where we want to pause and think about where we are right now. So the moles of zinc cancel and the moles of electrons cancel. Now we want to find the amps, so we need to divide by seconds. So let's convert 56 minutes into seconds. We know that all we need to do is multiply 56 by 60. So that's 3,360 seconds. So if you want to get amps, we need to divide by the time in seconds. So notice that the units seconds cancel, and so we're left with amps. And that's going to be the current that passes through the anode to the cathode by means of the wire. So 1.43 grams of zinc divided by 65.39 times 2 times 96,485 divided by 3360. So the current is 1.26 amps. And so that's the answer for this problem. Number 3. How long will it take in hours for a current of 745 milliamps to deposit 8.56 grams of chromium onto the cathode using a solution of chromium 3 chloride? So feel free to pause the video and try this problem yourself. By the way, if you want more examples, particularly multiple choice questions on chemistry, if you're preparing for like a final exam, check out 2 videos. One of the videos that I've created, General Chemistry 2 Study Guide Review, and there's another one on General Chemistry 1 Study Guide Review that I've created as well. So you can check that out, and it has a lot of multiple choice problems, and you can get more practice on these questions if that's what you're looking for. So let's go ahead and begin with this problem. So we're looking for time. Let's start with the mass. So there's 8.56 grams of chromium, and we need to convert it into moles. So the molar mass of chromium is 52. So 1 mole of chromium atoms has a mass of 52 grams. So the units grams cancel. And now we need to convert moles of chromium into moles of electrons. So let's write the half reaction for chromium. Notice that chromium is in the +3 oxidation state because there's 3 chloride ions attached to it, and each chloride ion has a charge of -1. So this is a reduction half reaction. So chromium +3 is going to need 3 electrons to turn into chromium metal. So the molar ratio is it's 1 to 3. So for every mole of chromium that is deposited onto the cathode, 3 moles of electrons passes from the anode to the cathode. So now the units moles of chromium cancel. So now we can convert moles of electrons into amps times seconds. So 1 mole of electron is equal to 96,485 amps times seconds. Now because we're looking for time, we want to cancel not the seconds but the amps. So what we have is a current in milliamps. 745 milliamps is the same as 0.745 amps. To convert from milliamps to amps, you need to divide by 1,000. 1 amp is equal to 1,000 milliamps. So we're going to divide by 0.745 amps. And so at this point, we have the unit in seconds. Moles of electrons cancel as well. So now we need to convert seconds into hours. So we know that there's 60 seconds in 1 minute, and there's also 60 minutes in 1 hour. So now this is going to give us the answer. So it's going to be 8.56 divided by 52 times 3 times 96,485 divided by 0.745 divided by 60 and divided by 60 again. So the answer that you should have is about 17.77 hours. That's how long it's going to take to deposit 8.56 grams of chromium if we use a small current of 0.745 amps. Consider these 4 standard reduction potentials. Now, what I want you to think about while I write these reactions, I want you to identify which species has which species is the strongest reducing agent and which one is the strongest oxidizing agent. Now, the cell potential, or the standard reduction potential for aluminum, is negative 1.66 volts. For Fe, it's about negative 0.44, I believe, somewhere around there. For copper, it's positive 0.34, and for silver, it's about 0.80 volts. So, now there's 8 species here. There's the 4 metals on the right side, and the 4 metal ions on the left. So out of these 8 species, which one is the strongest reducing agent? And which one is the strongest oxidizing agent? So if you place the cell potentials in order, the strongest reducing agent is going to be the metal on top. Metals are usually reducing agents, and metal ions or metal cations, which are the ones on the left, they are oxidizing agents. So a metal can't really oxidize anything, because for something to be an oxidizing agent, it wants to gain electrons. Metals, they want to give away electrons. So therefore, by definition, metals which give away electrons are reducing agents, and metal ions, which wants to acquire electrons, are oxidizing agents. So if you understand that, the most powerful reducing agent is going to be something on the right side, and the most powerful oxidizing agent is going to be one of these metal cations. Now, the most powerful reducing agent is the one who really wants to give away electrons, and that's going to be aluminum, because if you reverse the reaction, it's going to be the most spontaneous reaction. Aluminum wants to give away 3 electrons, and the cell potential is very high. It's positive 0.166. The higher the cell potential, the more spontaneous that reaction is. And that's why aluminum is the strongest reducing agent out of everything that's listed here. So what about the strongest oxidizing agent? The strongest oxidizing agents, they like to acquire electrons. And so it's going to be one of the metal cations. So it's going to be one of these ions on the left side. So which one wants to acquire electrons? The one that wants to acquire electrons is the one with the most positive cell potential, and that is silver. The Ag plus ion really wants to acquire electrons, and it has the highest cell potential when the electrons are on the left side. And so Ag plus is the strongest oxidizing agent. So let's try another example problem. So magnesium 2 plus 2 electrons will turn into Mg, and zinc 2 plus 2 electrons is going to turn into zinc, and then Pb2 plus 2 electrons will turn into Pb. Now for magnesium, I believe the cell potential is around negative 2.37, and for zinc, negative 0.76, and for Pb, things like negative 0.13 or 0.14. Now, so given the standard reduction potentials, where the electrons are all on the left side, which of these 6 species, which one is the strongest reducing agent? So if you're looking for the reducing agent, you need to look at the metals. Metals are reducing agents, because reducing agents, they tend to give away electrons. So which of these 3 metals is the strongest reducing agent? Now, for it to be a reducing agent, we have to reverse the reaction. So it's going to be this one, magnesium. It's never going to be the one in the middle if you place the cell potentials in order. So it's going to be either the one on top or the one on the bottom. So magnesium is going to be the strongest reducing agent, because when you reverse it, the cell potential is going to be very high. It's going to be positive 2.37. And notice that as you reverse it, the reaction changes from reduction to oxidation. Whenever the electrons are on the right side is oxidation. Notice that magnesium increases from 0 to plus 2, so it's being oxidized. The substance that is being oxidized is also the reducing agent, and that's why we can say that reducing agents, they give away electrons, and metals usually are the ones that give away electrons, so metals are usually reducing agents. So the best reducing agent is the one that's going to give away electrons, or the electrons are going to be on the right side, and it's going to have the most positive cell potential. So that's how you identify the strongest reducing agent. The strongest oxidizing agent, compared to all the reactions that are listed here, it's going to be one of the 3 metal cations, but it's the one that is most positive or least negative. So in this case, it's going to be Pb2 plus. And so this one is the strongest oxidizing agent because it's least negative or most positive. So it's more likely to pick up 2 electrons than any of the other 2 metal cations. So now we're going to try another question, but instead of dealing with metals and metal cations, we're going to deal with nonmetals and nonmetal anions. So I want you to identify the strongest oxidizing agent and the strongest reducing agent. The cell potential for iodine is about 0.54, and for oxygen, under acidic conditions, it's 1.23 volts. And then we're going to have chlorine and also fluorine as well. So at this point, as you probably noticed, the strongest oxidizing agent and the strongest reducing agent is not going to be in this reaction or in this reaction if you put the cell potentials in order. It's going to be in a reaction with the lowest cell potential and with the one with the highest cell potential. Now, reducing agents likes to give away electrons, and oxidizing agents likes to acquire electrons. So the oxidizing agents are going to be the ones on the left side, because these nonmetals, they like to acquire electrons. Nonmetals are usually oxidizing agents, and metals are usually reducing agents. Now on the right side, the nonmetal anions are going to be reducing agents, and metal cations are oxidizing agents. So if it has a negative charge, typically it's more likely to be a reducing agent than an oxidizing agent, because if it has a negative charge, it doesn't want to acquire more electrons. Rather, it may want to give it away, and so it's going to behave more as a reducing agent. So just to review, metals, neutral metals are reducing agents, neutral nonmetals are oxidizing agents. Metal cations, that's metals with positive charges, those are oxidizing agents, and nonmetal anions, which are nonmetals with negative charges. Those are reducing agents. So which one is the most powerful or the strongest oxidizing agent? We said that nonmetals are oxidizing agents. So which of these have the most positive cell potential? It's none other than fluorine. Now, to identify the strongest reducing agent, we need to look at the nonmetal anions. And so the nonmetal anions, the one that is the strongest, it's going to be basically on the other side. So it has to be this one. It's never going to be the ones in the middle. It's always the ones at the opposite ends. So iodide is the strongest reducing agent. Because if we were to reverse all the reactions, iodide will be the most positive or the least negative. It's going to be negative 0.54. And negative 0.54 is less negative than negative 1.36 or negative 2.87. So iodide is the strongest reducing agent, and fluorine is the strongest oxidizing agent. Now let's say if you're given two half reactions. Let's use Fe3 plus an electron, which turns into Fe2 plus. The cell potential for that is 0.77. And let's use nickel 2 plus 2 electrons, which turns into nickel. And let's say that's negative 0.23 volts. So if you're given these two half reactions, how do you calculate the cell potential? And also, how do you write the cell notation for this reaction? So I want to do some practice examples on this, because you know how to calculate the non-standard cell potential, you know how to find delta G, you know how to find K, but we should work on a few more examples on how to calculate the standard cell potential. So we have the standard reduction potentials where all the electrons are on the left side. We need to reverse one of them, because whenever you have a redox reaction, one has to be oxidation, the other has to be reduction. So the electrons, they cannot be on the same side if we're dealing with a galvanic cell, or any cell for that matter. So which one do we need to reverse if this is a galvanic or voltaic cell? If it's a galvanic cell or a voltaic cell, the overall cell potential has to be positive. So if we reverse this reaction, it's going to be negative 0.77, and if we add that to negative 0.23, it's going to be negative overall, so we don't want to do that. Rather, we want to reverse this reaction. So if we reverse it, it's going to be nickel, which is converted into a nickel 2 plus 2 electrons, and the cell potential is now going to be positive 0.23. So if we add these two, the overall cell potential is 1.1 volts. But we do have to balance the reaction though. Since we have 2 electrons on this side and only 1 in the first half reaction, we need to multiply the first half reaction by 2. So now the number of electrons are equal, so we can add the 2 half reactions to get the net reactions. So these will cancel, and so it's going to be 2 Fe3 plus Ni, and that's going to turn into Ni2 plus 2 Fe2 plus. So that's the net reaction. So the ions are in the aqueous phase, and nickel, which is in a metal, is in a solid phase. By the way, which reaction occurs at the anode and which reaction occurs at the cathode? So we need to know which one is oxidation and which one is reduction. Anytime the electrons are on the right side, it's oxidation. And if the electrons are on the left side, it's going to be reduction. And keep in mind, oxidation occurs at the anode. So this is the anode half reaction, and reduction always occurs at the cathode. So this is the cathode half reaction. So now that we have this information, we can write the cell notation. So if you wish to write the cell notation, the left side is going to be the side for oxidation, and on the right side is for reduction. So it goes from anode to cathode. So let's start with the anode. So we have nickel, which is the anode, and it's a solid. And then to separate the phase, we need a line. And then we have the nickel 2 plus cation, and that's in the aqueous phase. And now, to separate the oxidation and the reduction half reaction, we need to use a double line, which represents the salt bridge. Now, on the right side, notice that we have two ions, Fe2 plus and Fe3 plus. And they're in the same phase, so we got to separate them with a comma. So it's going to be Fe3 plus, comma, Fe2 plus. And they're both in the aqueous phase, which typically you should write that as well. So basically, what is the cathode? Because the cathode can't be an ion, it has to be like a solid. And we don't have two solids in a net reaction, we only have one. So in that case, we need to use an inert or non-reactant or non-reactive electrode. So you have some choices. You can use platinum, you can use palladium, you can use carbon graphite. So in this example, I'm going to use platinum. So platinum is going to be our solid electrode. And so this is the cell notation for this particular reaction. But let's try another example. Consider these two standard reduction potentials. So chromium 3 plus 3 electrons, and that's going to turn into chromium metal, and the cell potential for that is negative 0.74. And we're going to have a chlorine gas plus 2 electrons, and that's going to turn into 2 chloride ions. And the cell potential for that is going to be positive 1.36 volts. So this is a gas, and this is a solid. And whenever you have an ion, it's going to be dissolved in a solution. So first, what we need to do is balance this half reaction, or these two half reactions, and we want to calculate the net cell potential. So which reaction do we need to reverse? We don't want to reverse the second half reaction because it's going to be negative 1.36, and if we add that to negative 0.74, it's going to be negative overall. So for a Voltaic cell or a Galvanic cell, we want the overall cell potential to be positive because the reaction has to be spontaneous. So let's reverse the first reaction, and at the same time we're going to multiply it by 2 because to write the overall net reaction we need this to be 6 electrons. And because we have 2 electrons on the second reaction, we need to multiply by 3 so we can get 6 electrons. The least common multiple between 2 and 3 is 6. And so that's why we want 6 electrons so that they can both be equal. So let's reverse the first reaction and let's multiply by 2. So it's going to be 2Cr, and that's going to turn into 2Cr3 plus 6 electrons. Now, even though we multiply the reaction by 2, the cell potential doesn't change. We shouldn't multiply that by 2. But when we reverse the reaction, the cell potential will change sign. It's going to flip from negative 0.74 to positive 0.74. However, it's not going to be 0.74 times 2. It doesn't work that way. For chlorine, we need to multiply by 3, so it's going to be 3Cl2 plus 6 electrons, which turns into 6 chloride ions. And the cell potential is going to remain the same. It's going to be positive 1.36 volts. And we shouldn't multiply by 3. So now let's add these two half reactions. So the electrons will cancel, and so the net reaction is going to be 2Cr solid plus 3Cl2, which is a gas, and that's going to turn into 2Cr3 plus, which is in the aqueous phase, and plus 6 chloride ions, which is also in the aqueous phase. And the cell potential for that reaction is going to be 0.74 plus 1.36. So the total cell potential is 2.10 volts. Now, which reaction occurs at the anode and which one occurs at the cathode? So anytime the electrons are on the right side, it's going to be oxidation. And if it's on the left side, it's reduction. And keep in mind, oxidation occurs at the anode, so chromium is associated with the anode, and reduction occurs at the cathode. So chlorine is associated with the cathode. So let's make some space. So now, how can we write the cell notation for this reaction? So let's start with the anode side, the oxidation part of the reaction. So we have chromium metal, and we're going to separate this solid with a line, and this is going to turn into chromium 3+, which is in the aqueous phase. So next we need a salt bridge, which is represented by the two lines in the middle. And so now we're finished with the oxidative part of the reaction. That is the anode part. So now let's move on to the cathode, or the reduction side of the reaction. So we have chlorine gas, and we need to separate the gaseous phase from the aqueous phase. So chlorine gas is converted to the chloride ion, which is in the aqueous phase. And notice that for the cathode, for the reduction half reaction, there's no solids, so there's no electrodes. So we got to add an electrode. Last time we used PT, platinum, but this time we're going to use a different inert electrode. So we're going to use graphite, which is composed of elemental carbon. So we're going to use carbon-based graphite for the cathode material. And so this is the cell notation for this particular galvanic cell. So that's how you can write it. By the way, notice that we didn't put a 2 here. We shouldn't include any coefficients in the balance reaction in this cell notation. Now there is something else I do want to review, and that's the order in which we wrote it. So we had oxidation on the left side, and for the oxidation half reaction we started with chromium on the left, which is here, and then we moved on to the right side, which has the chromium +3 ion. And then for the reduction half reaction, we started with Cl2, which is on the left side, and then on the right side, as we go from left to right, we have the chloride ions, which there was a 6, but we didn't put a 6 in front of it. It wouldn't be proper. And then, since there's no solids, we know this is a gas, and this is aqueous. We had to include another electrode. In this case, we chose graphite. So now you know how to write the cell notations for different types of electrochemical cells. So now what we're going to do is we're going to focus on balancing reactions under acidic and basic conditions. So let's say if you're given this reaction. I should have done this before, but better late than never, right? How would you balance this redox reaction first under acidic conditions and then under basic conditions? So let's start with iodide. Iodide is going to turn into I2. Now the first thing you want to do is you want to balance the atoms. We have 2 iodine atoms on the right side, so we need to put a 2 in front of I- on the left side. Now the next thing we need to do is we got to balance the charges. Notice that the net charge on the right side is 0, but the net charge on the left side is -2. 2 times -1 is -2. So how many electrons do we need to add? The difference between 0 and -2 is 2. So we need to add 2 electrons. But to which side? Now we have to add the electrons to the side with the higher charge. So that is the right side. 0 is higher than -2 on the number line. So we're finished with that half reaction. Because the electrons are on the right side, we know that this half reaction is an oxidation half reaction, which would occur at the anode. So now let's balance the second half reaction, the reduction half reaction. So chlorate is going to be reduced to chloride. So under acidic conditions, we are allowed to add an H plus and H2O to balance the reaction. So we have 3 oxygen atoms on the left, so we're going to add 3 water molecules on the right to balance the number of oxygen atoms. And so once you balance the oxygen atoms, next move on to balance the hydrogen atoms. Since we have 6 hydrogen atoms on the right side, let's add 6 hydrogen ions on the left. So now all of the atoms are balanced. So now we got to balance the charges. What is the net charge on the right side? The net charge on the right side is -1. And the net charge on the left side is 6 times 1, which is 6, plus the -1 charge from the chlorate ion. So the total charge on the left side is +5. So now what is the difference between 5 and -1? If you subtract these two numbers, 5 minus -1 is 6. So that means we need to add 6 electrons to the side with the higher charge. And since the left side has the higher charge, we're going to add 6 electrons to this side. So now, what we need to do, we need to make sure that the number of electrons are the same on both sides. So we have 6 electrons on the second reaction and 2 on the right. So we need to multiply the first half reaction by 3 so that the number of electrons will be equal. So it's going to be 6I minus and 3I2 plus 6 electrons. So now what we can do is we can add these two half reactions. So the number of electrons will cancel. And so it's going to be 6H plus ClO3 minus plus 6 iodide ions. And that's going to yield chloride plus 3 water molecules plus 3 iodine molecules. So this is the net balanced reaction under acidic conditions. Now, if you want to balance it under basic conditions, you want to start with this half reaction that we have here. So here's what we need to do. We need to add hydroxide to both sides of the reaction. So notice that we have 6 H plus ions. We need to get rid of all of the hydrogen ions because it should only be present under acidic conditions. So let's go ahead and add 6 hydroxide ions to both sides since we have 6 H plus ions on the left side. So H plus OH minus, these two, they're going to combine and form H2O. So on the left side, we should have 6 water molecules plus 1 chlorate ion, 6 iodide ions, and everything is going to be the same, but we're going to have an additional 6 hydroxide ions on the right side. So now, notice that we have water on both sides. We have 6 water molecules on the left, 3 water molecules on the right. And we need to subtract both sides by the smaller of these two numbers. So let's subtract both sides by 3 H2O molecules. So this is going to disappear. Now we're going to have our final net reaction under basic conditions. So it's going to be 3 H2O plus chlorate plus iodide and so forth. So this is the net balance reaction under basic conditions. So let's check our answers. Notice that we have 6 hydrogen atoms on both sides. We have 6 iodine atoms on both sides, 3 times 2 is 6. 1 chlorine atom, and we have 6 oxygen atoms here. We got 3 in chlorate and 3 in water, so that's 6. So all of the atoms are balanced. The next thing we need to look at is the total charge. So here, this is -1 and -6. And on the right side, we have a -1 charge for the chloride ion and -6 for the hydroxide ion. So the net charge on both sides is -7. So the atoms and the charges are balanced on both sides. So we know this is the right answer. But let's go ahead and try another example. So try this one. Let's say if we have iron metal plus permanganate, and this is going to turn into the manganese 2 plus ion plus the Fe3 plus cation. So go ahead and balance this reaction first under acidic conditions and then under basic conditions. So let's begin. Fe is going to turn into Fe3 plus, and we need to balance the charges by adding 3 electrons to the side with the higher charge. So we're finished with the oxidative part of this redox reaction. So now let's move on to permanganate. Let's balance it under acidic conditions. So we have 4 oxygen atoms on the left side, so we need to add 4 water molecules on the right side so that the number of oxygen atoms are balanced. Next, let's balance the hydrogen atoms. So we have 8 hydrogen atoms on the right side, so we need to add 8 to the left side. So now let's consider the charges. The total charge on the right side is positive 2, and on the left side we have 8 times 1, which is 8, plus negative 1, so that's going to be plus 7 for the total charge on the left side. So 7 minus 2 is 5, so we need to add 5 electrons to the side with the higher charge, and that is the left side. So this is the reduction half reaction, since the electrons are on the right side, on the left side, excuse me. So now what we need to do is make sure the number of electrons are equal. The least common multiple between 5 and 3 is 15. So to get to 15, we need to multiply the first equation by 5 and the second equation by 3. So for the first equation, it's going to be 5Fe yields 5 Fe3 plus ions plus 15 electrons. And for the second equation, it's going to be 15 electrons plus 24 H plus ions, and then 3 permanganate ions, and that's going to turn into 3 manganese 2 plus ions and 12 water molecules. So now what we can do is add these two reactions. So let me put that up here. So on the left side, we're going to have 5 Fe plus 24 H plus and 3 permanganate ions. The number of electrons will cancel, and on the right side it's going to be 5 Fe3 plus ions, 3 manganese ions, and 12 water molecules. So this is going to be the balanced reaction under acidic conditions. So under basic conditions, what we need to do is we need to add 24 hydroxide ions to both sides to balance it under basic conditions. And so these two will cancel, and they're going to turn into 24 water molecules. So it's going to be 5 Fe plus 24 H2O molecules, and everything else is going to be the same, but on the right side we are going to add 24 hydroxide ions. Now there's one more step that we need to take care of, and that is the water molecules. So we need to subtract both sides by the smaller of the two numbers, so that there's going to be only H2O on one side of the reaction. So these two will cancel. So now what we have left over is going to be 5 Fe plus 12 H2O molecules and 3 permanganate ions, and that's going to turn into 5 Fe3 plus ions and 3 manganese 2 plus ions and 24 hydroxide ions on the right side. So now this reaction is balanced. So that's how you can balance it under acidic and basic conditions. So let's say if we have an electrochemical cell. So we have a power source, and we only have like one beaker instead of two. And let's say that the electrons are flowing from the left side to the right side. So with this information, and let's say that the solution contains copper sulfate and hydrochloric acid. With this information, how can you determine which reactions are occurring at the anode and at the cathode? You can also use the standard reduction potential. And if you don't have it with you, these are the important reactions that you need to consider. So hydrogen can pick up 2 electrons and it can turn into hydrogen gas, and the cell potential is about 0 volts. Now, this is the standard reduction potential for copper, and it's about 0.34 volts. Now, the standard reduction potential for oxygen under acidic conditions is about 1.23 volts. We also have the reduction potential for chlorine, and it's going to turn to chloride with a cell potential of 1.36 volts. And also sulfate can be reduced to sulfur dioxide under acidic conditions. And sulfur dioxide is polar, so it can dissolve in water. And the cell potential for this part is going to be 0.17 volts. So with these reduction potentials, which one is going to occur at the anode and which will occur at the cathode? So go ahead, take a minute, pause the video, and see if you can figure this one out. So let's begin. Let's identify the anode and the cathode first. We know that oxidation occurs at the anode, reduction occurs at the cathode. So we know that also electrons flow from the anode to the cathode. So the anode is on the left side, and for this example, the cathode is on the right side. The cathode doesn't always have to be on the right side. Sometimes it can be on the left. Just keep in mind the electrons flow from anode to cathode. So, which species do we have in the solution right now? In the solution, we have H plus ions, we have chloride, we have copper 2 plus, and we also have sulfate. So, which of these four species is most likely to be reduced? So if it's going to be reduced, that means that it's gaining electrons. The hydrogen ions are capable of gaining electrons. The same is true for copper. Sulfate can gain electrons, but chloride doesn't want to gain electrons. So chloride will not be reduced, because if it gains electrons, it will be like Cl minus 2, and that's not possible. So out of these three species that we highlighted, H plus, Cu2 plus, and sulfate, which of those is most likely to be reduced? So this is when we need to look at the cell potential. So which one has the highest or most positive cell potential? It's going to be copper 2 plus. It wants to gain 2 electrons, and the cell potential is higher than H plus or SO2, or SO4, sulfate. So therefore, this is going to be the reaction that occurs at the cathode. This is the reduction half reaction. Now all of these are reduction potentials. Now we know that oxidation occurs at the anode. So at the anode, we need to reverse one of these reactions. So H2 can't occur at the anode because we don't have hydrogen gas in the solution, so it can't be this. We got to look at the left side. Now we do have water because this is dissolved in water, so water could be oxidized to oxygen gas. It could go to the left, so we need to look at that. We do have chloride. Chloride could be oxidized to chlorine gas. For oxidation, electrons are lost, so if we reverse it, it can be an oxidation reaction. We don't have sulfur dioxide, so we can't use the third reaction. So it's either going to be, we can't use the fifth reaction. We could use the third one. I meant to say the third, not the fifth. So it's either going to be water or chloride that we can oxidize. So if we reverse those two reactions, which one is better? If we reverse H2O with O2, it's going to be negative 1.23. And if we reverse the chloride half reaction, it's going to be negative 1.36. In actuality, because these values are relatively close to one another, both of them can occur, but it's going to be easier for water to be oxidized to oxygen than chloride because it takes less energy to oxidize water into oxygen gas. So why can we say that? To oxidize chloride into chlorine, we need at least 1.36 volts. But to oxidize water into oxygen, we only need 1.23 volts. So that's why it's easier to oxidize water into oxygen gas. But both will occur. So, at the cathode, copper is going to reduce into, or be reduced into copper metal. And at the anode, oxygen, or rather water, is going to be oxidized into oxygen gas plus hydrogen ions, and it's going to give up 4 electrons. And the cell potential for that is negative 1.23. So these two reactions will be the predominant reactions that are occurring at the cathode and the anode. However, the other reactions can occur. So chloride can be oxidized into chlorine gas because the cell potential is not too far away from that with water. Now, sulfate can also be reduced at the cathode as well because the cell potential is pretty close to that of copper. But it's going to be easier to reduce copper 2+ instead of the sulfate ion. As you can see, the cell potential is not too far away. But if you just want the best reactions, it's going to be H2O. H2O is going to be oxidized at the anode, and copper 2+ will be reduced at the cathode. Those reactions are the most favorable reactions that will occur at those two electrodes. The others may occur, but just in a lower yield. They're just simply less likely to occur, but they can still happen. They can still occur. So that is it for this video. Thanks for watching, and have a great day.